All right, we got to start to discuss two more questions. And here we want to emphasize the more complicated one. And we do want to discuss this first. All right, so we want to set up and evaluate the double integral for x over this particular domain D, which is not explicitly given, but instead it is given by the enclosure of three curves. So we gotta make sure we know where are the curves and how do they intersect. And then with those information, and hopefully we can find the domain integration first, and then decide how to set up the iterated integral for the calculation, right? So first of all, for x equals 1, oh, sorry, x equals 0. X equals 0 is this vertical line, right? And then we also have the y equals 1. Y equals 1 is here. It is supposed to be a straight line. Wait, let me, okay. And how about the curve in the end? The 5 minus x squared. Well, when y equals 1, um, when y equals 1, we have 5 minus, I guess we need 4, so x has to be 2, right? So we know this curve is going to be intersecting y equals 1 at this point, x equals 2, y equals 1. And when x equals 0, where this y? I think we have 5, so this is a 5. I think the curve looks like this. All right, so the domain for integration, I think, is here, bounded by those three curves, x equals 0, y equals 1, and this parabola. Okay, so we want to set up the double integral in this region. How do we do? Well, we have to determine dA. Remember, dA is always either dx dy or dy times dx. So here we can treat this as either a type 1 or type 2 region. So if we do treat this as type 1 region, and then we are going to determine to integrate about the y variable in the interior integral and the x variable for the exterior integral, right? So here, what are the limit for the x and the y accordingly? For x, we can see because this point is 2, 1, so x will start from here. X is going to start at 0 and stopped at 2. And how about the y? Y will be starting from this horizontal line, y equals 1, and stop at this curve. Remember, this curve is y equals 5 minus x squared. So the y is having the lower limit 1, and the upper limit for y is 5 minus x squared. All right, so with this, we can see this is what we set up. And we can also treat this as a type 2 region, which means we integrated this horizontally, right? And then if we do that, let's just do that. If we want to do that, we have to integrate about the x variable for the interior integral, and we have to integrate the y variable for the exterior integral. And the y is obviously starting from y equals 1 to y equals 5. So that's relatively easy. And how about the x? x is going to start from here and stop at the curve also. So x is going to, x left is starting at 0, but how about the x right? For getting x right, we need to solve this in terms of x and pick the right branch. So we need to know y equals 5 minus x squared. So x equals x squared equals 5 minus y. So x equals square root 5 minus y. There's a plus or minus. Obviously, here we want to choose the plus. So the upper limit or the right limit for x is indeed positive square root 5 minus y. Okay, so this is the first question. Well, first question we want to discuss. Obviously, it's a little bit easier. It looks a little bit easier to evaluate this integral by using term, which is square root. We don't want to have this square root to do the integral. So how about we just stick with this formula and compute the integral. All right, and now we want to switch the gear a little bit, and how about we discuss question 7. The most important part of finishing this question is to identify where the domain is in terms of the polar coordinates. But because the domain is actually given in the Cartesian coordinates, so how about we just try to write it down in the Cartesian coordinate first. Obviously, we can see for x and y has to be what? For x and y has to be following the description is a third quadrant bounded by 2 circles. Bounded by 2 circles means we have to, so this is the lower limit, right? And this is upper limit. So we do have the first description. If we do think about the, well, maybe it's better for us to draw this diagram. Okay, so what this is, and what this is, we have 2 circles. The first circle is having the radius 2, and then the second circle is having, the first circle is having radius 2, the second circle is having radius 3. Okay, so for the radius 2, radius 3, and another thing is that the region we're only interested in the part that bounded in quadrant 3, which is here, right? It's only this piece. So we now know the x and y description for the domain should have x squared plus y squared that is between 4 and 9. Why that? Well, this is the key feature of this region is that if we pick any point, we computed x squared plus y squared value, and it is a bounded between this outer circle and the inner circle. So that is described in this statement of the question. All right, so that is why we have this piece, but we also have another piece, which is both x and y should be negative. Which fit the description of the third quadrant. So this is the whole description of the domain in the Cartesian coordinates. You can see how complicated it is, right? But the question is, can we convert this domain D and in the polar coordinates? The answer is yes, because we can see if we do want to represent this in the polar coordinates, we do see the polar angle for this pink region will be between what? Between pi and 3 pi over 2. So all the points in the pink region will have the feature their polar angle will be between pi and 3 pi over 2. Right? Well, if you have a we look at another piece of this Earth, or you would see that you have to specify the polar angle accordingly. For example, in the first quadrant, the polar angle will be between 0 and pi over 2. Okay, so now we know the polar angle for the pink region. And how about the radius r? Well, the radius r will be between 2 and 3. Right? How do we get that? Well, actually, if you take the square root, because x squared plus y squared is bigger than 4, which means square root of x squared plus y squared is going to be bigger than 2, which is this one, and accordingly this one. So the pink region is indeed a so-called polar rectangle. And now we can rewrite this. Okay, well, obviously we also need to convert x squared plus y squared. Remember, x squared plus y squared is equal to r squared. So this x squared plus y squared is converted into r squared. And how about the dA? dA is, as we remember, r times dr d theta. Okay, so this is becoming r times dr d theta. And we are integrating r as in the interior integral. Theta is for the exterior. So theta is between pi and 3 pi over 2. R is between 2 and 3. So this is what we have. Okay, so indeed, we have theta equals pi to 3 pi over 2. R equals 2 to 3, r cubed, dr d theta. So this is the integral we need to set up. All right, we can compute this. This is r to the 4 over 4 for r equal 2 and r equal 3. And theta is between 0, not 0, but a pi to 3 pi over 2. So what do we have? What we have here, yes, 3 to the 4 over 4 minus 2 to the 4 over 4. And then theta between pi and then 3 pi over 2 d theta. We have 3 to the 4, I think, is 9 squared, which is 81 over 4 minus 2 to the 4 is 16. This is the 4. And the antiderivative for this constant in terms of theta is theta. We have theta equals pi, theta equals 3 pi over 2. So we get 81 over 4 minus 4 times 3 pi over 2 minus pi, which is half pi, right? 81. Well, what is 81 minus 4? 81 over 4 minus 4? This is right? So 81 minus 16 is 65 over 4 times pi over 2. So this is 85 pi over 8. So this is the answer. All right. Um, do you want to study the question 8? Maybe you can give the answer quickly if you could. How about let's do that. Consider this. Let's sketch the domain and set up the and evaluate the integral. Well, we can evaluate this integral for sure, right? We can set up the integral for sure first. So I is f r theta dA. What is the dA? dA is supposed to be r times dr d theta. And here f is, well, f is constant too. Okay, so 2 times r is our is what we get. Well, not so maybe we should think about this carefully. So the dA is this piece, the integrand is this piece. Okay, and then we have our r for the interior integral, theta is for the exterior integral. So theta is specified with pi over 2 as lower limit, pi as upper limit, and the r is starting at 1 and stop at theta squared. So this is not too bad, right? We can compute this relatively easily. So 2r as the integrand here. The antiderivative is r squared, and r is 1 theta squared d theta. So this is what we have. Well, maybe we need to do a little bit more calculation to finish this up. So we have theta squared and then squared minus 1 squared d theta. Theta is from pi over 2 pi, and we have to find the antiderivative of this, which is the polynomial in terms of theta. We can figure this out, right? Well, how about we finish it here? So I equals theta equals pi over 2 pi. This is a theta to the 4 minus 1 d theta. The antiderivative is theta to the 5 over 5 minus theta. So this is what we have. So we got pi to the 5 over 5 minus pi, subtract pi over 2 to the 5 over 5, subtract pi over 2. So this is what we have. And you can simplify, but this is essentially what we should have for this question. All right, let's stop here.